Hello everyone. Let us take the example of the domain of marketing. In it, we study consumer attributes that are not directly measurable most of the time. For example, let us take consumer attitudes, consumer satisfaction, and consumer intention to buy any product. So, what we do is we take help of certain items which we hope that they reflect the actual underlying attribute or construct or the dimension. But before we do any kind of analysis, we need to be sure that the items that we have are considering that it is representing the underlying attribute is actually representing it or not. So for that there are a couple of techniques, and there are two types of factor analysis, which are exploratory factor analysis and confirmatory factor analysis. For today I will be discussing exploratory factor analysis on a conceptual basis, and also I would like to demonstrate it quickly in using our software how it is done for one or two examples. Okay, so let us begin. The first thing is what it is. What is it? So factor analysis is used to identify the number of dimensions reflected by a test, the meaning of those dimensions, and the degree to which dimensions are associated with each other. Okay. There are three important questions regarding a test dimensionality. The first very important question is how many dimensions are reflected in the test items. So if we say that I generate a 30 item questionnaire, so out of these 30 items, how many underlying dimensions or attributes are there? Are there 1, are there 2, are there 3, or are there more? This is the first question. The second question is, if a test has more than one dimension, are those dimensions correlated with each other or not? Okay, so if the correlation exists, then the analysis is slightly different. If it doesn't exist, then the analysis is slightly different. The third point is, if a test has more than one dimension, what are those dimensions? The test items or the constructs that are identified by the software, it will not name them. It is up to us, for the researchers, to identify and name them based upon the properties that we can see of those items that we have recorded. So generally speaking, this is an arrow directionality in factor analysis, that the arrow points from the attribute to the responses, and they represent the idea that the psychological attribute or the dimension or the factor affects the response to test questions. Okay, so whatever person is giving, suppose on a scale of Likert scale, on a scale of 1 to 5, 1 to 7, whatever you have recorded, the assumption is that because the underlying attribute is influencing the item and not the other way around. Okay, so though we are not able to gauge the attribute directly, but based upon the scoring on that item, we can indirectly measure how much the psychological attribute is present within that respondent. So beginning with the unidimensional test. So if the answers to each of the questions of the test are affected by only one psychological attribute, factor, or hash dimension, such a test is called multidimensional test, as it reflects only one psychological dimension or attribute. So what happens is, here is the test items or questions would have the property of called as conceptual homogeneity, because the responses to each item would be a function of the same psychological attribute. For a unidimensional test, only a single score is computed, reflecting the single psychological attribute measured by the test. And how that score is computed is, all the item scores are combined in some way, usually through averaging, summing, or counting to form a composite or a total score. For unidimensional test, reliability and validity should be estimated and evaluated for the total score produced by the test. So small example, let us see in the next slide. So suppose there is a psychological attribute that we have taken, and we have said that there are 6 questions that were asked. Let us say there are 6. Okay, there is slightly type error. Let us say there are 5 items. So 5 items are getting asked over here. The person responds on a scale of 1 to 5 for each item, and let us say for item there is 3, 4, 3, again a 4, and maybe a 5. So if we are going to do based on summing, we have to add all of these items. So just quickly summing, 4 plus 3 is 7, 10, and 19. So we will say the average comes to total comes to 19, If we want to go the average pathway, then we will say the average is 19/5. Okay, so this is the way we will compute the total score based upon the our goal. Either we can sum it, we can average it in this case. Okay, from unidimensional test we move to multidimensional test. So as the term implies, multidimensional means there will be more than one dimension. So when a psychological test include items that reflect more than one psychological attribute or the underlying construct or the dimension, then the test is called multidimensional. Multidimensional test with correlated dimensions can produce a variety of scores. So first thing is, each subset has its own subset score. So what we mean by this, suppose again the example of 1 to 30. Let us say there are 5 dimensions. Roughly, let us say on an average they have equal items, so each dimension will have 6 items. Okay, so 5 dimensions become 30 items. So what this point means, say that because there are 5 different dimensions, 5 different constructs or 5 different factors, so the 6 items that are associated with that particular dimension of single dimension should get summed and or averaged, and that will produce, each subset has its own subset score. Okay, second point is, each subset is itself unidimensional, because in itself taken out from all the 30 items, only those 6 items will have become a unidimensional. And the question is, each subset are conceptually homogeneous. In addition to scores for each subset, multidimensional test with correlated dimensions. I will soon say that there are correlated and uncorrelated. Right now assume that the 5 dimensions that you are having, okay, so they are correlated. By this we mean that, and that let us say dimension 1, dimension 2, dimension 3, dimension 4, dimension 5, they have their respective scores, let us say by summing, and then the correlations are calculated between these, and this correlation is present. So if this correlation is present, then what is going to happen is, multidimensional tests with correlated dimensions are often scored in a way that produces a total score, which is like sum of sum. Okay, so each dimension is already a sum of 5 to 6 items, and then sums of sum simply is meaning sum of all the 30 items. So that will produce a general psychological attribute or a second or a higher order total score that is combined across several subsets or specific psychological attributes. Okay, I hope this point is clear. From here I move to the next slide, that a multidimensional test could have some subsets that have reasonable psychometric quality, means reliability and validity, and other subsets have poor psychometric quality. So therefore each subset requires psychometric examination separately. Then the total score also requires psychometric evaluation for correlated multidimensional tests. In terms of use of multidimensional test offers a variety of options. So test users can use any or all of the subset scores depending on their relevance to research or practical context. Next comes this multidimensional test with uncorrelated dimensions. Now uncorrelated dimensions means the 5 or 6 dimensions that we have seen in the previous slide, they are not correlated to each other. So if test dimensions are not associated with each other, then the test can be considered as a multidimensional test with uncorrelated dimensions. Here test takers receive scores, one for each dimension as by a summing or averaging, and each one is itself treated as it were unidimensional, because if it's not correlated, it doesn't matter if you take the responses separately or combined, it is not going to matter. So such a test could be viewed as a set of unrelated dimensional tests that have their items mixed together. And for tests with uncorrelated dimensions, no total score is computed. Only you check the psychometric quality of reliability and validity for the unidimensional aspect of each dimension that is within that multidimensional test. Do not compute the total score in this case. Graphically or in image we want to see, this is a left hand side image is a multidimensional test where the latent constructs or the psychological attributes are not correlated. There is no linkage over here. While over here you can see that the attribute A is formed by 3 questions, attribute B is formed by another 4, 5, 6, another set of 3 questions. So these were the individual unidimensional test, but because they are these two are having correlation is present over here, so their scores can be combined to form a higher order level construct that is called a journal psychological attribute. This is specific, this is journal, their scores get combined, while in uncorrelated they are not getting combined. Moving ahead, so as we start our exploratory factor analysis, the first step is to choose an extraction method into it. The software will ask you. So this refers to the specific statistical technique to be implemented, and there are multiple options, but the most common option is the principal axis factoring that I am going to use for today. Others are mentioned on this slide, like maximum likelihood factor analysis and principal component analysis. It is helpful to reverse code any negatively keyed items before conducting an EFA. So if in our item scale was some items was negatively keyed, you please convert it into the other way around to record it. After the first step, once you have decided the extraction method, which we are going to do the principal axis factoring, the second step of EFA is to identify the number of factors within the set of items. Okay, so we direct the statistical software to extract that number of factors once it is decided how many factors we need to extract. How we can do this? This is the next explanation coming up. So to address the number of factors issue, test developers and test users often refer to statistics called eigenvalues. Research has said that it has been criticized, and eigenvalues, the rule was use eigenvalues greater than 1, but it has been heavily criticized. So a second and a much better way to determine the number of vectors is to examine the relative sizes of the eigenvalues. What I mean by that is our ability to compare the relative sizes of eigenvalues can be enhanced by graphically plotting those values. Such a plot is called a Scree plot. Let us see on the next slide. So this is an example of a Scree plot which is fairly simple to interpret. So what is happening, as you see on the x-axis, these are component number, dimensions, or the factors, whatever you want to say. So this is 1 factor, this is 2 factor, it is saying the 3 factors, so on and so forth, and then these are the eigenvalues that has been plotted. So what we to identify how many factors, how many dimensions to extract, what we have to see is where the difference between these points taper off and becomes non-significant. Here it is large, here it is large, but after this it starts to become similar kind of differences. Okay, so as the slide is also saying, when examining a Scree plot, we look for a relatively large difference or drop in the plotted eigenvalues. So here this difference is large, and after this there is a significant drop and it is tapering down. So we will say that 1 less from where this taper down begins. So that is where we will say, in this case we will go with 2 factor solution, and that is some of the most common ones that are done. But it can happen that the graph is very ambiguous, the differences are not significant, the relative sizes are not difference coming significant. What we can do, such cases are called ambiguous cases, so where the Scree plot is not helpful. So what we can use is additional information to guide understanding of the scale's number of dimensions. So one type of additional information is the clarity with which the scale items are associated with its factors. So what we do is, suppose we say that okay, extract with 2 factors and the solution is not coming, so we say that go and do with 3 factors. We again say that go and do with 4 factors. So we say that we extract different number of factors and proceed again to the next step, and our results from the later steps that are followed in the EFA might motivate us to revisit the present step depending upon how the output is coming. And this to and forth, so this to and fro and or back and forth nature of the EFA can be used to solve this dilemma. Occasionally it can also happen that we simply do not obtain a clear answer to how many dimensions question, suggesting that scale has no clear dimensionality. Okay, so if we did encounter that situation, then we might conclude that the scale needs revision, for example in terms of clarifying the construct that it is intended to assess, or in terms of devising the items themselves. Okay. So moving ahead, if the evidence suggests that data scale is multidimensional, okay, it's not unidimensional. If the scale is multidimensional, that means there is more than one dimension that exists in the items that you have just taken that data for. What we use is usually rotate the factors. Okay. So the purpose of this step of rotation is to clarify the psychological meaning of the factors. Factors, underlying construct, or the dimension, one and the same thing. There are generally two types of rotation. First is the orthogonal rotation, and what it does is it generates factors that are uncorrelated, or we say it's orthogonal to each other. Within it, the procedure is called the Varimax rotation, and is the most common subtype of orthogonal rotation. The second type of rotation is called the oblique rotation, and oblique rotation gives the freedom to the dimensions to be correlated or uncorrelated with each other based upon the data that is collected. It doesn't force fit for them to be uncorrelated as is it getting force fit in orthogonal rotation. Within oblique rotation, there are many subtypes, and it includes Promax and direct oblique. Generally, a researcher should use oblique rotations as their preferred types of rotation, because you can see they give the freedom for the dimensions to be either correlated or uncorrelated based upon the trueness or the actual data collected. What the data, let the data speak. That is our point. The association between items and factors is important over here, right? So items are item 1, item 2, item 3, and this is your dimension or your construct or your factor. Yeah. So EFA represents these associations in terms of factor loadings, and each item has a loading on each factor. So generally factor loadings range between -1 to +1, and they are interpreted as correlations or standardized regression weights. Generally it is preferred that loadings above 0.3 or 0.4 are often seen as reasonably strong, while loadings as high as 0.7 or 0.8 are very strong. Means either way, means plus minus both ways, -0.3, -0.4 also, +0.7 or -0.7 or -0.8 also. So when using orthogonal rotation, we obtain loadings that can be seen as correlations between each item and each factor. But in the case when using oblique rotations, you obtain several kind of factor loadings, that not only one set, but there are 2-3 sets of loadings. So first is pattern coefficients and structure coefficients. There are two types of coefficients you will get. So how to interpret the factor loadings? Interpreting factor loadings, two pieces of information are very critical. First is the size of the loading, and that indicates the degree of association between the item and the factor, as we saw that ranges from -1 to +1. So those loadings that are close to -1 or +1 indicate a stronger association between the item and the factor. Second is the direction of the loading. Is it a plus sign or is it a minus sign? So a positive loading indicates that people who respond with a high score on the item have a high level of underlying factor, versus a negative loading indicates that people who respond with a high score on the item have a low level of underlying factor. So moving ahead, there are three matrices. I will have a sample example on the next slide or in 1 or 2 slides. So the factor matrix represents the factor loadings that would be obtained before rotating the factors. So this is not very useful, because it is telling the loadings before any rotation is done. The results are not that clear, and the usefulness of factor rotation, because they are very useful, you generally ignore these first set of loadings. Pattern coefficients reflect the unique association between an item and a factor, and that is pattern coefficient represent, please pay emphasis on the word unique, that reflects the degree to which an item is associated with a factor, controlling for the correlation between the factors. Okay, so what does this simply means is that before doing the correlation between the item and the factor, what you do is you run a regression analysis between the factors itself. Okay, so suppose you want to do it for F1 and item 1. So what you need to do is, first you will run a regression between F1 and F2, and then the residuals that come, that residual is getting correlated with item 1, and that is why it is saying that controlling the correlation between the factors. This is how it is done. And in contrast, structure coefficients are simple correlations between respondent item and their level of underlying factors, that is, there is no controlling done for the correlation between the factors. So this is an example. The software will give you all the three outputs. These two, this one and this second, are both rotated. This is totally needs to be ignored, and this is where the correlation between these two in pattern matrix or pattern coefficients, the correlation is getting controlled, while in the structure matrix or structure correlation coefficients, the correlation between these 1 and 2 factors is not controlled. Results will look similar, but the values will be over or under inflated in structure matrix, while this will be better. On a rough eyeball tracking, we can see that for this particular example, these two factors, item 4 and 5, go well with factor 1, while other 3 are going well with factor 2. So we can say 2 factor, while item 4, item 5 goes with factor 1, and for factor 2, item 1 and 2 and 3 goes. Okay. So this becomes a preferred way. Within this the structures, simple structures occur when each item is strongly linked to only in one factor. In the previous slide, I show you that linkages are fairly strong, but you see that item 2 is having 0.04, and there is minor. Something neat, ideal information, ideal scenario can be exactly perfectly 0, but still they are very close to 0. So that's not an issue, but a very simple structure occurs when each item is strongly linked to one and only one factor. And failing to find a clear solution by visiting the number of factors, there is at least one additional step that can be done. Okay. So what you can do is you can drop the items that are causing the trouble. So we might drop items that have poor structures, and this might suggest that item reflects a psychological construct that differs from the ones reflected by other items from the scale. Very correct. That maybe this item is not actually representing the psychological construct, because the assumption is that whichever psychological construct, dimension of factor, and the items that it is representing. So if it is, the score is getting, let us say on a scale of 1 to 5, a person is giving a 4 on this, and if the underlying dimension or the factor is the same, so for the other, the scores should be same, almost same. So if it is not happening, means that underlying factor that troubling item represent is not the one which you think, and for that you can drop it. Also, another problem when an item loads robustly on more than one factor. Suppose it loads on 2 factors, it is coming 0.6, 0.6 both on factor 1 and factor 2. What it can happen is, this means that the item is affected by both these dimensions, and because of that it's not good for us. So such an item does not uniquely reflect any construct, and thus we might drop it or revise it to reflect only one construct. Okay. The whole goal is the items should uniquely reflect the underlying dimensions of the construct. There should be no cross loadings. That is the thing. So this is an idealized factor structure. This is a very simple structure, because you can see very clear cut loading is there, other things are 0. Okay. So this is idealized, but in realistic it's fine to find weak loadings, but there should be clear cut strong loadings. This is what we will find in our real life situations. But in case suppose this was a 0.7, then it's not good. Then we need to check the items, or we need to do some revisions, some dropping, something needs to be done. Okay. So I hope this is making sense. And now we move to the total scores computation. So we should create total scores for multidimensional scales only when dimensions are correlated, as I discussed earlier, and with each other to a meaningful degree. There should be correlation to a meaningful degree, and generally like 0.3 is fine enough. Anything above 0.3 is fine enough. So rotation does not alter the correlations among the items, and thus it does not alter the empirical facts in our analysis. Somebody may think that because of rotation we are trying to do a cheating, but it's not that. It doesn't influences the empirical facts of analysis, so it is fine. And when factors are correlated with each other, they are not at 90 degrees. So the image is coming up soon. This is becomes a perfect 90 degree for a two factor solution, factor 1, factor 2. When they are graphically plotted, it becomes orthogonal, while if we say it is like this, when it is less than 90 degree or something else, then it becomes a correlated factors. And in contrast, if factors are uncorrelated, they can be plotted at 90 degree angle. This is the image. So here this is unrotated factor structure. You can see it is totally unsure that are these items close to here, this is here. It is not making sense. To correct this issue, what we are doing is we are rotating the factors. This is orthogonal rotation. You can see this is a 90 degree angle, better than the previous one, but still there is no strong loading. You can see some factors are very strongly loaded, some items are very strongly loaded on some factors, but this becomes a confusion. This is 0.4 and then there is a scale. This has become a confusion over here. Versus you see the third one, the obliquely rotated factor structure. This is a very clear demarcation that these couple of items go here, these couple of items go here. Okay, so moving ahead, so there is slightly typographical error, and this should be positive side. Okay, -1 to +1. So and so forth needs to be adjusted. So this was the basic theory behind the factor analysis, and the source that I was using it, the book of Furr, RM Furr, Psychometrics and Introduction. Now what I will do is I will move to the R software and will demonstrate over there how quickly to do this factor analysis for a simple example. Okay, so heading to R software now. So I have already prepared an R script for you to run quickly, and to run this factor analysis in R you will needing the help of the psych package. So if you are not there, first you can run this thing, install that packages called .psych, and it will install the package. Once the package is installed, what you need to do is you have to run the library psych function. So once this is done, this library package, psych package, will be activated. After that, for doing exactly the factor analysis, first you need to insert like something like either the items, and the intermediate stage will be always there should be a correlation matrix. So right now what I am doing in this EX1 matrix is that I am feeding a correlation matrix. So this is how this matrix is fed. It is actually an identity matrix, so lower and upper half are actually simple, and this is one of the simple structure where either the items will perfectly load or items will not perfectly load. This is a hypothetical example. So there are 6 items I am telling you, and to execute it I am executing the EX1 matrix step, and now this matrix has been saved but the names have not been given. So the next next line, call names E matrix 1, will assign the names of the variables, let us say in order are talkative, assertive, outgoing, creative, imaginative and intellectual, to be assigned to the respective columns. So these names are now assigned, and moving ahead, what we need to do is to see the first step, how many factors to analyze. To do this, as you recall, I told it that we need a Scree plot. Okay, and before that, the thing that is not accepted is the eigenvalues. So these are the eigenvalues. So the old rule said eigenvalues greater than 1. So you can see 2.194, 2.17, and the values are here. Just okay. So now to develop the eigenvalues, so I have run this value. So we see that 2.194, 2.17 as they are visible. So eigenvalues greater than 1, we have an initial hunch that they can be 2, but as we discussed, that Scree plot is the better one. To obtain the Scree plot, this is a this is the equation or the command that we are going to write, at vss.scree for that particular matrix, and now this matrix has come up. Okay, so now you see the relative sizes are first, second, there are huge relative size differences there, and then the taper off happens. So 1 less after the taper off happens. So the component number from 3 we say 1 less. So we say that it is a 2-factor solution. Now moving ahead to run the actual factor analysis that is run in this line EXL1 out. Assigning to FA is for factor analysis. We are saying that for the matrix that we have just stored, EX1 matrix, do the factoring method is principal component analysis. PA n factors means the number of factors that you need to run, that we have from the Scree plot we are saying we are 2, and rotation because we want the it will be oblique rotation, so we are saying do it for Promax. And once this is done, I'm going to run this and we will have our output over here. We can print the output using this print EXL1 out, and in a sort is a true. So this is the way the output comes, that factor analysis using method principal access factoring. That couple of things that you need to see, because this output is very detailed, but for the brevity of this discussion, you see that intellectual, imaginative, creative, assertive, talkative, and outgoing. So these are the items that we have fed, and these are the PA1 and PA2, factor 1, factor 2, and you can see that 0.94, 0.7, 0.6, 0.0000, and so we can say that intellectual, imaginative, creative becomes one set, and assertive, talkative, outgoing becomes other set. Also, the other thing that becomes important is this portion where factor correlations. You can see that there is no correlation among the factors. Okay, moving ahead, quickly showing you the second part in which there is a similar matrix that is fed, but here there is some correlation exists between the items also. So I will do the same steps. I will quickly run the first two steps, so that the new matrix is stored, and now I will generate the eigenvalues. Now this eigenvalue still suggests that 2.74, 1.53, the values greater than 1, but to be sure that I will use the Scree plot. Now you see the Scree plot is different from the previous one. There are two relative sizes falls, and from the third again the relative sizes tapers down. So we say that the number of solutions can be 2 in this case also. We run a similar formula using factor analysis of principal component analysis. No, not principal access factoring, sorry for my mispronunciation. Principal access factoring, and n factor is number of factors equal to 2. So we are running this, and now we are getting the output. So now you can see that there in the previous output there were perfect zeros, 0 0 0 0 0 0, but now there is some correlation that is present for all the factors. It is still there is some items are having very strong, others are next to 0, so we can comfortably ignore that. But now because some correlation exists between the factors, and we can see that PA1 and PA2 have a 0.35. so now if you want, we can club the scores of these two to make a higher order construct if we need. Okay. So I hope this brief discussion of exploratory factor analysis and its how to run it in R has helped you, and I will try to make something on confirmatory factor analysis. So it's very soon. So that's it from my side for today, and I wish you best in your research endeavors. Thank you.